Hello, good morning everyone. Today, inshallah, we will try to cover a very important lecture. We will talk about the service integration as an application, as we did previously. Finished all of this and we went through it. The previous couple of lectures are really very important to handle the line integration, the service integration, the treble integral, the meanings, the volume, everything. Also, going through the integration through a main region, making substitutions, using the parameterization, all of this is really very important. Today, I will do some sheet applications and solve more problems for practicing this part. I will start this lecture with just reviewing some of the information that we did go through. So I would like to start with this slide. All of these slides, you will find them in the previous sessions. So you will be in a very good shape. If any part of this lecture is not clear enough or need more clarification, please do visit our previous lectures. You will find every part of this lecture explained and clarified in a very good way. Now I want you to remember evaluating an area of a service. I believe we had this part with the triple integration, by the end of the triple integration, or with the application of the triple integration. It's evaluation of the area of a part of a graph of a function. Let's say z equal f of x and y. So we are talking about certain service. That's over above the flat region D. In order to evaluate this surface area, okay, all I have to do is to just substitute in this level. So this is how to evaluate an area of a part of a graph of a function that's over or above, okay, the flat region D. All I have to do is to find the value of f, determinant, very good. Then find the partial derivatives of f with respect to x, with respect to y, making substitution, remarking the domain, and starting your integration. Okay, of course, the double integration. For the surface integrals, if sigma be a regular parameterized surface, so if I have sigma and it is already parameterized, so using the vector equation, which is r, the values of the parameterization is u and v, since you are in dime 3, so it will depend on two vectors, for example. So x is a function u and v, y similarly like, z is a function in u and v. So these are the variables of this region. So all I have to do if I want to find the surface area on the surface is to just use the parameterized form. So I'm getting the value of f as a function in the vector equation. So I will make the replacement. Instead of having x, y, and z, it's going to be an x in u and v, y and z similarly like. Then I will multiply it by the value or the magnitude of the vector that I will have from the cross multiplication of the derivative of the vector equation with respect to the first parameterized variable and the second parameterized variable. All I have to do simply is to find r, which is the vector equation of your surface, then start differentiating r with respect to u, with respect to v, make this cross multiplication, and then you will have your vector, then start getting its magnitude multiplying by f. And we will see a couple of problems on this, I believe, with the beginning of our application in this lecture, inshallah. As I told you, the area of the surface sigma is given by, that's the area of sigma, which is going to equal to the integration on the element of the surface. This is if I want to evaluate the surface area. Okay, the area of S also can be given by the, as we spoke in the previous slide, by the root of 1, the derivative of f with respect to x is the derivative of f with respect to y, once f is given as a scalar function, as you saw in the previous slide. Okay, once more, of course, I want you to remember that the multiplication of partial r, partial v, partial r, partial u, it will give you the normal vector on these two directions. For a flow of a vector field or the flux of a vector field, F across a regular surface sigma, oriented by the normal vector into the surface defined by, simply I will do the dot product between the vector field and the direction vector perpendicular, which is N. Of course, the principal unit normal vector to a parameterized surface is really very easy to evaluate if R is the equation vector of the surface. So all I have to do, as we saw in the previous lecture, in the previous slide, that I can make the cross multiplication with the partial derivatives of R with respect to U or with R with respect to V, as you can see. Then I will be able to get the unit vector perpendicular on this surface, which is simply gonna be the cross multiplication divided by the magnitude of this vector. Of course, for the flow across a parametric surface, while sigma is the surface, if R is the equation vector of this surface, and if N is given, so all I have to do, you have the vector field, all I have to do is to do this multiplication. Of course, you know this vector is also, I've given you, it's the value of the unit vector, so multiplying them together will cancel the magnitude from these two parts, and this is going to be the equation that I will follow. And also we will see a bunch of problems on this application today, so it's going to be easier. I believe as much as you solve, as much as you will feel it's really very simple, comfortable around these integrals, and you will know the slight differences between if you have f as a scalar value or if you have f function as a vector field and you want to evaluate the flow of this vector field or to evaluate the flux of this function. In negative, of course, that's the positive direction. In the negative direction, you will have the same equation, same everything, but you will have the opposite direction. And we already spoke about this plenty in the previous lecture, going through the surfaces which you have an outer surface and an inside surface, orientable or non-orientable. We did go through all of this in the previous lecture. Okay, very good. Another thing that I want you to remember, that the link between the contour integration and the surface integration. Here, there are two possible relationships between the orientations of sigma and c, where sigma stands for the surface or the part of the surface of this quadratic, and the c is the contour around this surface, as we saw in the previous lecture. Of course, if I'm moving on the contour with my left hand inside the region, this is the positive direction, and that was explained explicitly in the previous lecture. So as you can see, the lady here is trying to move around the counter, so with her left arm inside the region, that's the positive direction. Of course, the negative direction will be her right arm is inside the region of the surface. And Stokes' law states that if I want to evaluate the surface integration for this closed surface, so if you read it once more, let sigma be an oriented surface with edge C oriented positively according to sigma. So for every vector field, F of class C1 is defined on an open set containing sigma, I can replace the surface integration by the contour integration according to this relation. So instead of dealing with a surface integration, I can do the contour integration also very easy. And we will see, of course, applications also on this problem today. That's the rotation or the curve of F and N. Okay, the Gauss divergence also, it's really a very important slide, and it's very important part of the surface integration. If you have the vector field given by the three components in the 3-die, it's all, of course, a C1 class functions, which means it's differentiable with the first derivative, at least. and containing G and N in the unit vector exterior to the normal vector. So it's really very simple that instead of doing the surface integration, we can do triple integration for the divergence of F. And if you remember the divergence of the vector field, it's very simple. All I have to do is to get the derivative of these components with respect to X, Y, and Z, adding them together in this manner. This is the divergence of F, and then substitute and evaluate the your integration, triple integration on this surface. So now you can see that with the surface integration, I have plenty of options. That will be we should choose the correct one or the suitable one based on your equation, based on the nature of your F, if it was a scalar value, if it was a vector field, based on the domain and the simplest way to handle it. Within the coming problems, that's the sheet number 10 or set number 10. It's the last in our course, and I wanted to go through it with you to make your life easier. So all I need you to do is to grab a paper and a pen and start, after reviewing and seeing these problems, try to do it on your own. You will discover the differences between if you have F as a scalar function, if you have F as a vector field, if it is required to find the potential, the flux. Of course, you will have to review all of these definitions before you start, or you will be facing each problem solved by a different method, and you are not going to be able to recognize the differences and or the why we are doing this. So it's very, very important that you first go through the main stuff first of all, then, or the main slides for each part, then summarize them beautifully, then try to solve these problems as you will see. I will start this set or this list by some problems as you will see. The first of them is asking you to determine the surface integration for a certain function, which is f, x, y, and z, over the surface parameterized, okay, by R, such that the domain is a subset of from R2 into R3. Once he stated that, I will need to focus sure about the domain and how I'm going to handle it. In the following cases, and he's giving you 3 problems. Let's start with problem number 1. He is giving you f, x, y, and z. Stop. You have now your f function. This function, you have to think, is it given to you as a scalar value or as a vector field? This is a scalar value function, so you can see here it's an xy plus z, so it's actually mapping from R3 into R, from R3 into R. You will have to memorize this. And of course, the vector equation that's controlling the domain is given by uv, u plus v, which is a parameterized form. So your vector field, your vector equation controlling the surface is giving you parameterized. And the function is a scalar. And he wants you to evaluate this guy here with this, which is the surface integration. So I will start with the surface parameterized by u and v. And the scalar function f, x, y, and z. So all I have to do is to do the surface integration, making the substitution of the f with respect to the R equation or the vector equation of the surface, times the magnitude of the cross multiplication with respect to the partial derivatives of R with respect to u and v. And this is really very simple. So I will have to identify R, and the R is given here by this vector. Let me grab a pen. So actually, this is R. It is given to you. So all I have to do now is to get R, finding partial R, partial U, partial R, partial V, which is really a very simple task to do, as you can see. I will start differentiating with respect to U, which means it's going to be 1. With respect to U, the V component is going to be 0. With respect to U, also it's going to be 0 and 1. And that's for the first vector, or the first partial derivative. For the second partial derivative, I will do the same, exactly the same. but with respect to v, so you will have 0, then 1, and 1. As you can see, these are the values of the partial derivatives. Now all I have to do is to find the cross multiplication. So partial r, partial u cross r sub v. I can write it this way. It's gonna be an I, j, and k, and start putting your numbers. I'm sure you are damn good in all of this. You have finished your course in linear algebra, so you are very good to go. So once we get f of, this is the main function, that's r, so, and it is defined for this region. Partial derivatives are already here, 1, 0, 1, 0, double 1. Start making the substitution through the determinant, as you can see, of this matrix. Making the cross multiplication. If you remember how to proceed to cross multiplication, all I have to do is just getting I, cancelling the first column and first row. So it's gonna be a 0 minus 1, so it's gonna be a negative. Then minus of a j, closing the second rows and columns. Then I will have 1. So, okay, so it's gonna be 1. But then plus a value of a k, also the same way like I will close the first row and the second column, so I will have 1. So it's gonna come up to negative 1, and 1, as you can see. That's the cross multiplication. I will need the magnitude of this vector. Do you remember how to get the magnitude? Of course you know. The square of the first component plus the square of the second component plus the square of the third component under the square root. So simply, I got the magnitude, as you can see. So it's going to come up to root 3. I'm ready to rock. All I have to do is to replace this guy by root 3, and then making the substitution, getting f as a function in u and v. So all I have to do now is to take this f function, replacing x by the value, replacing y and z. Of course, this stands for x, that stands for a y, and this guy here for z. Just making the substitutions, as I told you, it's really very simple, a piece of cake. Once you make these substitutions, you will have uv plus u plus v. So here's the integrand in front of you. All I have to do the integrand, root 3 du dv. Now, I've given you the domain. The domain is 0 and 1 to the power of 2, which means you will integrate from 0 to 1 in the direction of u or v, and from 0 to 1 in the other direction. It's a very simple task. Once you do it, it will be, it's obvious, it's going to be really very simple. And I'm sure you can do it on your own for the double integration, because we already did go through this plenty of times. But just for the simplicity and just gathering the information, okay? And to be sure that you are following me correctly, so this is 0 and 1, 0 and 1. The integrand here, I have root 3, which is going to be outside. I have u dot v plus, you have u and v, that's the v, that's the u. I will integrate with respect to u, then with respect to dv, as you can see, it's a piece of cake. So integrating with respect to u, it's going to be v times u squared over 2. Then the v will be v times u plus a u squared over 2. Then I will make the substitution from 0 up to 1. Then I will integrate with respect to 2 dv from 0 to 1. So all I have to do is to replace every value of u by 1, which means this guy is going to be 1, that guy is going to be 1, and this is going to be 1 over 2. Then I will integrate with respect to v in the other direction. I will have v squared over 4 plus, this is going to be also v squared plus a half of a v. Then substituting from 1 to 0. Don't forget I have root 3 outside. So once you make the substitution, it's going to be root 3 multiplied by these values. As you can see, you can just replace every v by 1 and gather the values. You will have the value of your integration, which is really very simple task, as you can see. So, if you remark, based on the information gathered, I've started to determine which direction I'm going to follow, and so you will find the steps is really very simple. Once more, for the second problem, he's asking you here, giving you f of x, y, and z, which equal to y, and for the vector equation, which is u squared, u, and v, and giving you d, so it's gonna be exactly the same. I will go surface parameterized by r, and the scalar is given. So all I have to do is to follow the same recipe. I will have to get the cross multiplication first, getting the magnitude of this cross multiplication, then making the multiplication, as you can see. So here's f of x, y, and z equal to y. And of course, that's the vector equation. So I will need to find the derivative with respect to u, with respect to v, already done. These are the two derivatives. With respect to u, it's going to be to u 1 and 0. With respect to v, double 0 and 1. Make the cross multiplication, as you can see. So that's the value. I will get the magnitude of this vector. So it's going to be 1 plus 4u squared. Here we go. That's a 1 plus 4u squared. Now I'm ready. I have this part. All what's missing now is to make this substitution, which is really very simple. This is the x component, the y component, and that's the z component. As you can see, that's the x, y, and z. So all I have to do is to take the z component, which is, I will take the second component, which is u, just to put it here in f. So I will need to just do the double integration of u, which is the integrand, times a root over 1 plus 4 over u squared du dv, and he's giving you also the parameterized values from 0 to 1. Yes, we are right. From 0 to 1 to the power of 2. The idea here is to integrate this guy, and it's really very simple. You have 1 plus 4u squared to the power of half times u. So all I have to do is to multiply that guy here in 8 divided by 1 over 8. So now I have 1 over 8 double integration of an 8u, 1 plus 4u squared to the power of half with respect to du, with respect to dv, from 0 to 1, from 0 to 1. Start integrating, add 1 on this power and divide on the new power. So the integration will be 1 plus 4u to the power of 3 over 2 divided by 3 over 2. Then making the substitution from 0 and 1. Don't forget that you have 1 over 8 outside your integration. Once you finish, start integrating with the other dimension, with the other direction from 0 to 1, same way like. So I will replace u here by 1. So I will have 5 over 3 over 2 to the power of 3 over 2 times 1 over 8. Then I will integrate with the direction of dv and replacing by 1. As you can see, the steps are really very simple, but what's really matter from the beginning of this problem is to determine the scalar, integrand or the scalar function and the r direction, and then you are ready to rock. As I told you, f is equal to u. Then I will put u times the root of 1 plus 4u squared du dv. Already the region, it's from 0 to 1, which is a square in the u and v directions. Just to finish the double integration, as you see me doing, it's really very simple. The inner integration is really simple. All you have to do once more, multiply here by 8. Here is going to be 1 over 8, and then you will increase power 1 on the power of half, so it's going to be over 2 over 3. For the last part of this question, he is giving you f once more is equal to x squared. Now he is giving you r, the equation value, as cosine u, sine u, and v, and the dimension or the integration region running from 0 to 2 pi times from 0 to 2. So all I have to do simply is the surface parameterized by r, u, and v, and the scalar field, it's f function in x, y, and z. So here is the function. I'm integrating with respect to the surface. So I will get f as a function in u and v, and then multiplying as you can see in the determinant of this cross multiplication. So first of all, once more, here's R, as you can see. I will get partial R partial U, partial R partial V. Here's my two partial derivatives. That's with respect to U, that's with respect to V. I have them ready. I will do the cross multiplication, as you can see. Okay, after getting the cross multiplication, that's the vector that we are going to have. I will get the sum of the squares of these components under the square root. Here we go. That's the square root. 4 cosine square, 4 sine square, take 4 as a common, and under the square root, so it's going to come up to 2, as you can see. Now I have the value of the cross multiplication evaluated, which is 2. I will get f as r. So as you can see here, f is a function in x squared. I will replace x by 2 cosine u. As I told you, this component is x, that component is y, and this component is z. Just to make it the substitution, I will have 4 cosine square u 2 times du dv. And the domain is given in the direction of u. It will be running from 0 to 2 pi, in the direction of v from 0 to 2, as you can see. How to integrate cosine square? I know you know that. Of course, if I have cosine square u, I will have to replace it by 1 plus cosine 2u divided by 2. Then I will integrate this guy, which is going to be u plus a sine of a 2u divided by 2. Don't forget, all of this is multiplied by half. Then start, making the substitution from 0 up to 2 pi. Then integrate in the other direction of v and make the substitution from 0 to 2. It's very, very simple. So you will need, as you can see, I will have to go through all the processes, all the laws, and the major issue is to define. That's a scalar function, that's the equation vector of the surface. Step, I will go through this direction. This is what's really matter. I believe if you do a couple of problems from those types, it will be very easy for you. Okay, now going to the second problem. Here he is giving you S if the canonical surface with the equation Z x squared y squared. I'm giving you the Z function or the function controlling this surface. Okay, and there is a question here before I continue. You know what's this equation for. You need to, number one, review your parameterized session. You will find them in the lectures. You will need to go through the types of the surfaces, the various surfaces. When it's going to be a cone, when it's going to be a paraboloid, when it's going to be a cylinder. It will make a huge difference in understanding the limits or the boundary of your integration, as you will see. Okay, I will start with the first problem. That's a problem number 2, number 3. If I started with the first one, he's telling you, remember that if a surface is given by z, f of xy, scalar function, so that's, I can use this relation. Okay, if the surface is implicitly defined or parameterized, in this case, I can go through this relation, getting r as u and v, multiplying the u and v. So, based on the given, as you can see, I have here f not parameterized, so I would rather go with the first situation, as you will see. So z is x squared plus y squared. Below the plan z equal to 1. The first question is, what's that? Z is equal to the square root of x squared plus y squared. If you remember, that's going to be an equation of a cone. So squaring both sides is going to be z squared. Okay, I will move it to the other side, so I'll have x squared plus y squared minus z squared equals 0, which is an equation of a cone. And below the plan z equal to 1, so below the plan of z equal to 1, I'm talking about this part here, this small part or this tiny part. So now I'm ready to evaluate my integration, as you can see. So that's the cone, that's the plan, the intersection, and I need to identify or do the surface integration on the given domain. So all I have to do now is just determining the disk or the intersection here, which is gonna be a circle or an ellipse. In my situation, it's gonna be a circle which equal to 1. This is very, very simple. All I have to do is to get back to this guy, replacing z by 1. So I would have x squared plus y squared less than or equal to 1. So now it's determined. So the region is defined for me. It's a disk, unit disk actually. So I will need to make the substitution. That's f, which is root x squared y squared. So I will get f sub x, f sub y. I'm preparing to use this formula here. So I have z, which equal to the square of x squared plus y squared. So once you get z sub x, or you get z sub y. Differentiating with respect to x for this function, it will equal to half x squared plus y squared to the power of negative half times the derivative of what's inside this bracket, which is going to be 2x, which will leave you to, you are having x divided by the square root of x squared plus y squared. And that's for the z sub x. In a similar manner exactly, I will have half over x squared plus y squared to the power of negative half. But instead, I will have 2y, which is going to be y divided by the root of x squared plus y squared. Getting them both together square, you will find a surprise here. So if I'm trying to get this guy, which is 1 plus, I will get zx to the power of 2 plus zy to the power of 2. And that will leave me with 1 x squared over x squared plus y squared plus a y squared over x squared plus y squared, which is going to be 1 plus x squared plus y squared over x squared plus y squared, which means 2. Under square root for these values, it means I will have root 2. All of this is explained here, and it's really very simple. As I told you for 1,000 times, please do solve these problems with a pen and the paper and redo everything. As you can see, here is 1 f of x, f of y to the power of 2. You will end up having this guy, so it's going to come up to root 2. I'm ready to rock. All I have to do is to just make the replacement. It's going to be root 2 dx dy. The region is a disk, so it's really very simple to find its domain or to use the geometric properties of this unit function, of this unit circle. Otherwise, you can integrate. I will leave this guy to be, I will write it here, r dr d theta. I'm changing to polar coordinates since it's a disk. So I will go from 0 to 1, which is in the direction of r, and from 0 to 2 pi, I will end up with having the same thing, but just don't forget that it's multiplied by root 2. So you will have root 2 by exactly the same. Of course, I will integrate r, is going to be r2 over 2, so replacing the r by 1 is going to be a half. Integrating the theta, it's going to be theta. Substituting by 2 pi, the 2 will eat the 2, so you will end up having root 2 pi, as you would see. I'm sorry that I'm speaking rapidly, but I depend on that. I don't want you to get bored from this lecture, but I need you, as I told you, to be solved. Okay, once more, this is problem number B. He is giving you a paraboloid with the equation z. We shouldn't say that it's a paraboloid, but he already stated for you because you know the equation, so you will be able to discover the nature of this paraboloid, and it is below the z equal to 1. Also, I want you to remember the z function here is given, so I'm using this guy. I'm not going to use the other equation. Okay, once more. That's the equation of the paraboloid, which is a paraboloid symmetric about the z, and it's opened upward, as you can see. And now with z equal between half and 1. So actually, these are the value, or that's what's gonna happen. I'm sorry, where z is in the plane, below the plane of z equal to 1. So actually, I'm talking about this part here. So it is the paraboloid, and at z equal to 1, here is the plan. I'm talking about this guy. Okay. Once more, it's the paraboloid. I have z equal to 1, so if you make your substitution, you will be working with a disk also, x squared plus y squared greater than or equal to 1. I will need to get the partial derivatives, which is going to be easy peasy. This is going to be 2x when you differentiate with respect to x, and 2y with respect to 2y. All I have to do is to make the substitution, so it's going to be 1 plus 4 of x squared plus 4 squared. That's the result under the square root. So I can parameterize, of course, everything, or change the variables to be polar, because at the time being, I'm really ready to integrate. Here we go, that's the region, which is x squared plus y squared greater than or equal to 1. And this guy here is 1 plus 4 over x squared plus 4 over y squared dx dy. The better idea is to replace all of this into polar coordinates, okay? And this is what have been done here. These are from 0 to 1 for our direction, from 0 to 2 pi, since we are talking about the complete circle. So I will start integrating directly. Here we go. Replace to r dr, so it's going to be r dr d theta. This is 1 plus 4 r squared. And the integration will run from 0 to 1, from 0 to 2 pi, exactly as you can see. If I want to integrate, all I have to do is to multiply here by 8. Here is going to be 1 over 8. Now I'm ready to just have this guy here 1 plus 4 over r squared to the power of 3 over 2 divided by 3 over 2. Don't forget 1 over 8. Then make the substitution 0 and 1. Then finish everything by the outer integration from 0 to 2 pi. You are ready and you have your relation. As I told you, it's really very simple. So all I need is to complete this double integration, as you can see. For the last one, and it's going to come up to this value, I believe I sent you the PDF for these slides to be as a reference with you. For the last problem, it's going to be x squared y squared z squared